Welcome students to the series of lectures on statistics. And I'm very excited to tell that we have completed probability discrete distribution or discrete probability distribution and now entering into continuous distribution. If you remember our lecture where we introduced probability distribution, we said that there are two different kinds of probability distribution. One is discrete probability distribution, another is continuous distribution. Till now, we have covered discrete probability distribution in the curriculum of CFA and FRM, which is binomial, Bernoulli, and Poisson distribution. And we understood the probability mass function. We understood how to calculate the mean and variance. And we got to know the formula for mean and variance. Now the story changes from the continuous distribution. The story changes because whatever now you will study in the series of lectures of probability distribution, that you will definitely gonna be applying in your real world. Because in continuous distribution, you have uniform continuous distribution, you have normal distribution, you have t distribution, you have chi-square distribution, you have f distributions, and all these distributions are heavily used in finance in real world. And the problem is that you will find very few people having expertise of continuous distribution. Okay, so with that, we'll enter into our first distribution, that is uniform continuous distribution. What is the name? Name is uniform continuous distribution. Now, the question is why we are talking about uniform continuous distribution, where we should have started the conversation from normal distribution, because it's not easy to understand continuous distribution. There is something changes in the continuous distribution from the world of discrete distribution. So it is very, very important, very, very critical that you be aware of these nuances of the continuous distribution. Okay, and you will understand in like first 10 minutes that what are the difference between the discrete distribution, what I should not be using in continuous distribution that I studied in discrete distribution. And that's why we are starting from this basic distribution in the continuous space, that is the uniform distribution. Otherwise, we should have started from normal distribution or any other distribution. Okay, with that, let's enter into our uniform continuous distribution. Please remember it is not discrete, so the world is changing. In the uniform continuous distribution, first let's see the plotting of a uniform continuous distribution. The plotting of the uniform continuous distribution doesn't look like binomial or Bernoulli. It has something different. On x-axis, we have outcome. Actually, we don't need y-axis. I just plotted to make you feel comfortable. I don't need y-axis for my continuous distribution. I don't need it. So just focus on this line. This line is uniform. It's a horizontal line to the x-axis. And this is uniform. Why? Because the probability of this, every entity is identical. What is the probability? We'll talk about it. That's why it is uniform, a horizontal line. And it is not like this one point, another 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 point. No, it's continuous in nature. So the probability of A happening, say A is a number, say 4. What is the probability of 4.00001 happening? What is the probability of 0.2 happening? What is the probability of 0.3 happening? So on and so forth. It is continuous. Please do not make a mistake of making this plotting for a uniform continuous distribution. It is continuous in nature. So you cannot plot pointers like Bernoulli binomial or Poisson distribution. Understood? Now, because of that, because it is continuous in nature, one thing you will definitely not use in continuous distribution is probability mass function. You won't use it. It's useless. The reason is, what is probability mass function? Probability mass function used to give you what? Probability of a single outcome. In Poisson distribution, it was k. In binomial distribution, it was small x. Whatever. You're interested in finding what is the probability of a single outcome. What is the probability of 2 hits in 5 tosses? What is the probability of 3 hits in 5 tosses? That was a discussion of binomial distribution. And when we enter into the discussion of Poisson distribution, if you remember, we said what is the probability of 3 accidents in an hour? What is the probability of 5 calls in an hour? Remember? Now, if you try to find out the probability of one single outcome, what? One single outcome, it is useless. Because what is the formula for probability? The formula for probability is, give me 30 seconds. The formula for probability is the number of outcome in favor divided by total number of outcome. What is the total number of outcome in this space from A to B if A is 4 and say B is a number 10? So there is a uniform line between 4 to 10 which is representing probability, and you're interested in finding what is the probability of say 7. What is the probability of 7? Assume it gives some numbers like the number of outcome in the favor is say 10 or say 15. But what is the total number of outcome? The total number of outcome is infinite. Understand, there are infinite numbers here from 4 to 10. I just mentioned 4.0001, 4.0002, 4.003. I'm just counting 4, 5 zeros. What is 4.000, 10 zeros and then 1? There are infinite numbers. So the number of outcome in favor is what? Infinite. So if you're interested in finding the probability of one single event, which is the probability mass function, it is zero. It is useless. It is useless in what? Uniform continuous distribution? No, it is useless in all continuous distribution. It is useless in all continuous distribution. So, so you cannot use probability mass function, then what we can use? And I also mentioned that there is no use of y-axis. There is no use of y-axis. So how you will tell the probability? In the previous discussion, y-axis used to be my probability. Please check the lectures of binomial distribution. Y-axis was my probability. Now here I say y-axis is of no use, PMF is of no use. If y-axis is of no use, where you will mention the probability. The probabilities are mentioned in the continuous distribution in the area under the curve. What area under the curve? Area under the curve, this area, which is under the curve. Actually, it's not exactly under the curve. Let me plot it again. The area under the curve, the area under this horizontal line. This will tell me the probability. So area under the curve will tell me the probability. If I join these two concepts that, okay, you cannot use probability mass function. Okay, you cannot use y-axis as a probability and probability is area under the curve. Then this gave birth to something different than the discrete distribution, and that is called as probability density function. What? Probability density function. Probability density function, you are interested in finding the probability through the area under the curve, but probability of what? Probability of x between this and this, between certain two values. We won't write probability of x equal to say 3 because that would be 0 in the continuous distribution. So we will say, give me the probability between 5 and 8. Give me the probability between 7 and 9. Give me the probability between C and D. So give me the probability between C and D. So give me the probability between C and D. That is probability density function. This is useless. You cannot find the probability of 1 point because that will come to 0. And if I respect the concept of area under the curve, say I'm interested in finding the probability of one single event, say 7. What is the area under the curve of 7? This line, what is the area of line? As per geometry, it's 0. So I'm saying you have to use area under the curve to find the probability in continuous distribution. And then I'm saying, hey, find the area of a line for a single event, that will be 0, right? So you have to move to probability density function. And what probability density function telling you? Probability density function telling you, hey, you have to play between two pointers. You have to find the area between two events or two pointers. So I'm interested in finding the area between C and D. That's it. And it looks like a rectangle. So I need to know what is my length and what is my breadth. If I multiply my length and breadth, I'll get my area under the curve, and that is what my probability. That's it. That's it. If I know my length and breadth, if I multiply length and breadth, this will give me the area under the curve, and that is what my probability. We'll see how that will happen. Okay. So first of all, tell me, what is this area? What is this area? This area. What is this area? I'm saying the probability is identical or uniform between event A and B, or between number 4 or 10, or between number A and B. So I'm saying, what is this area? What is this area? See, this line ends at A and this line ends at B, first of all. There's no probability post B and there is no probability before A. As per this uniform line, as per this uniform continuous line, this line exists between A and B. So I'm asking you, what is this area? if the probability is area under the curve and the probability only exists from A to B, then this area has to be 1 because that is the total possibility. That is the total probability. And total possibility or probability is what? 1. So this total area is what? 1. 100% probability. Sum of all the probability is what? 1. If I'm saying area under the curve is the probability in the continuous distribution, so total area under the curve has to be 1. Because probability cannot be more than 1 or cannot be less than 1. The total probability cannot be less than 1 or cannot be greater than 1. It has to be 1. So that's what I'm writing here. Find the area under the curve. For that, first of all, say what is the total area? It is 1. Why? Because total area represent what? Total probability. I'm not saying about uniform continuous distribution, any distribution. Say there is F distribution. And if I say what is the total area under the curve, it has to be 1. If it is chi-square distribution, it is a continuous distribution. I'm saying area under the curve is probability. So what is the total area? It has to be 1 because that represents total probability. So area under the curve is 1. Okay, area under the curve is 1 when I know that the entity is between A and B. And I'm interested in finding what? I'm interested in finding what is the probability, what is the probability, what is the probability between C and D. I'm interested in this area. I'm interested in this area. Okay. If I say C and D is two numbers, say 5 and 7. So I'm aware of what is the length. The length is 7 minus 5, right? D minus C is the length. What about breadth? What is the breadth? If I know the breadth, I'll multiply the breadth with the length. I'll get what? The area under the curve. That's it. Okay, let's look into this area. This area is 1. So length into breadth is equal to 1. Length into breadth is equal to 1. Length is B minus A. Say A is a number 4, B is a number, say 10. So 10 minus 4, that is the length. So I'm saying B minus A is my length into breadth is equal to area, which is 1. So breadth is going to 1 upon B minus A. So breadth is going to be always 1 upon B minus A. The two extreme of the uniform continuous distribution. What is the two extreme of uniform continuous distribution? B and A. These are the two extreme. That is my length. But what is my breadth? Breadth is 1 upon B minus A. If breadth is here 1 upon B minus A, even in this case, the breadth is going to be what? 1 upon B minus A. I'm writing capital B for breadth. This B represent the number. This number. 10. Okay. So what is the area under the curve? D minus C into breadth. D minus C was what? Length. So D minus C into 1 upon B minus A. That is the area under the curve. And that is your probability mass function for X between C and D. You are interested in finding the probability between C and D. So probability mass function is the area under the curve for the section where X is greater than C and less than D. C and D can be any number. The final formula is D minus C upon B minus C. This is the formula actually written in your curriculum. And this is actually the formula for the probability mass function. Actually, this is not the unit formula. The unit formula is slightly different. We'll talk about the unit formula. But if they will ask you what is the probability that the value is between 4 and 7, 5 and 7, 6 and 7, then this is the formula that you will use. Okay. So for example, A was 4, B was 10, and I want to know what is the probability that the value is between 7 and 5. So it is 7 minus 5 upon what? 10 minus 4. That is my probability. Okay. So that is probability mass function. Sorry, probability density function. We won't use probability mass function. If I have incorrectly said probability mass function, we don't use probability mass function. This is probability density function. No probability mass function to be used in uniform continuous distribution. Okay. With that, there is another very important concept to remember in uniform continuous distribution. Even this concept lies in the discrete distribution as well. But we didn't discuss about this concept in discrete distribution because it's better to use the concept where it is actually required. So CDF is a very important concept in the continuous distribution? Yes, it does exist. CDF as a concept, PDF as a concept does exist even in the discrete distribution. But generally the application is very limited. In the case of continuous distribution, that's become pretty evident that you have to use PDF because you cannot use PMF. And CDF because it helps in prediction. It helps in prediction. You will see how. So what is CDF? CDF stands for Cumulative Distribution Function. Again, because the probability in the case of continuous distribution can be calculated only with the help of area under the curve. Only with the help of area under the curve. What is CDF? CDF stands for, if I say, give me the CDF for say a value 5, then you will say, give me the probability of X less than equal to 5. So you will try to find out all the probabilities for all the outcome less than equal to 5. The notation is capital F of X equal to small x. In our example, small x is 5. Or you can write probability of capital X less than equal to small x, where small x is equal to 5. So again, in uniform continuous distribution, I'm saying give me the probability of X, which varies from A to B, capital X, which varies from A to B, but give me only the probability of X less than equal to X, of X less than equal to X. This is the capital X. So you have to give me this probability. Now this makes sense in the continuous distribution because this again is the area under the curve. You have to find the area of this section. That's all. If you're able to find the area of this section, then you can find the cumulative distribution function or the value associated to the probability of X less than equal to small x or less than equal to 5. What was the breadth we calculated? The breadth was 1 upon the difference between the two extreme outcome, that is B minus A. What is the length here? That is X minus A. So X minus A upon B minus A. That is my cumulative distribution function. That is also a formula that is given in your curriculum, X minus A upon B minus A. Okay. So this is the PDF and CDF of uniform continuous distribution. Will you use uniform continuous distribution in life? Yes, you would. Whenever you are playing with random variables, whenever in Python you do NP random, or whenever you try to find out a random variable in your Excel sheet, you're actually using uniform continuous distribution because the probability of every outcome is identical in the nature. Whatever the probability is, it's very near to zero, doesn't matter. But they are using uniform continuous distribution at the back end. Definitely, yes, you can change that uniform continuous distribution random number generator from uniform to normal distribution or any other distribution. Okay, that is easy and most of the people are aware of it, that how you can generate a random number in normal distribution. Now, so this was the discussion of uniform continuous distribution, and this is the first distribution that we discussed in the continuous distribution space. And we introduced two concepts, PDF and CDF, super critical because this PDF and CDF will be used and discussed in all the distribution in the continuous space. One thing, I'm giving you the mean and variance. Why? Because the mean and variance is required for all the distribution, whether you talk about discrete, binomial distribution, Poisson distribution. We discussed about mean and variance in all the distributions. Now here I'm giving you the formula of mean, that is a plus b by 2, and variance formula is b minus a whole square upon 12. So I'm repeating, the mean formula for uniform continuous distribution is a plus b by 2, and the variance formula is b minus a square upon 12. In the next session, we'll derive it. The reason this derivation is important because this derivation of mean and variance required integration, and integration is the very important concept in the continuous distribution because the summation won't work. So you have to play with integration to find out your mean value, to find out the variance value. Okay. So in the next session, we will talk about how to find out mean and variance for uniform continuous distribution. So those students who are just interested in mugging up the formula of mean and variance can do that. But in the next session, we'll try to derive mean and variance for uniform continuous distribution. Okay. With that, I'll take a break. Thank you. Have a nice day.